Hey folks, how y'all doing? We're going to go ahead and look at the differences now between SHA-1 and SHA-2 today. I apologize in advance. Um, Not all of these videos are exciting, and this one is going to be just dull as dishwater because we've already talked about how SHA-1 works. Um, we just have to go over a couple of differences between these, but this should give you enough information that if you wanted to implement SHA2 yourself, you could go ahead and do most of the implementation. So there are 6 variations of SHA2, and the difference is the size of the message that they message digest they produce. We're going to start by looking at these two, SHA 256 and SHA 512. These are the two most commonly used ones. We've already talked about SHA1, which is broken. SHA1 uses 80 rounds of encryption and works with a 512 bit block size and can encode messages up to 2 to the 64th bits is your maximum file size, your maximum input size. The different variations of SHA2 were partially to allow for some backwards compatibility. SHA-256 is kind of a drop-in replacement for SHA-1. It still uses a 512-bit block size, and it uses the same message padding, which means it has the same 2 to the 64th bit input size because of the same padding algorithm. But it encodes a little faster. It's only 64 rounds. And so SHA-256 is a variation of SHA-2. I mean, all of these are variations of SHA-2. But it's sort of meant to directly succeed SHA-1 because it uses the same block size, it uses the same input size, and it's just faster and more secure. SHA 512 is a little bit more robust. It uses a 1024-bit block size, a new padding algorithm that will support up to 2 to the 128-bit input size. But because there's more data, it takes a little bit more computations to securely confuse and diffuse that much data. And so you go back up to the 80 rounds that SHA-1 had. So in the same number of rounds, you can hash much more data using SHA 512, or you can encode the same amount of data using fewer rounds using SHA 256. And so those are the two main variations of SHA-2, and we want to talk about those two first. So SHA-256 uses the exact same message padding protocol as SHA-1. You have seen these instructions already. They were in Monday's video. We append a 1 to the end of the message. We append enough zeros then so that the last block is 448 bits long. Then we put 64 more bits on there. 448 plus 64 is equal to 512. And these new 64 bits encode the length of the original unpadded message. And so the length is incorporated into the block size. There are some reasons for doing that have to do with trying to generate a collision by just taking the same message and like appending a few zeros to the end of the message. Zeros won't change the answer if you do any XORing, and it won't change the answer if you do any addition. And so putting a few zeros onto the end of a message might make it easy to create a collision unless you are altering the first block by actually encoding the length of the message into the message itself. And so that's what this step is for. There is a security reason for wanting to encode the length of the message into the message itself. It avoids collision by appending zeros to the end of a message. So SHA-512 changes these two parameters so that the message can be a little bit longer. We still have the same result that 896 plus 128 is 1024. But we're now using longer blocks, and we're now having a longer space to encode the length of the message. So that's not backwards compatible with SHA-1, but it does allow for much longer messages to be encoded. That is, and right now, sort of more of a theoretical advantage than a practical advantage, because there are very, very few applications where we would ever have to create a digest for a message that's this long. This would be just enormous, but we have this available for future expansion. All right, so then SHA-1 had an initial hash string. This was the string that had an equal number of zeros and ones. These are the initial hash strings for 256 and 512-bit mode. And if you'll notice that the 8 shorter blocks in SHA-256 are actually just the beginnings of the 8 longer blocks in 512 mode. That's not a coincidence that's what these blocks here are. So SHA-256 creates a 256 digest made up of 8 32-bit blocks. SHA-512 uses longer. I'm calling these blocks, I should probably call them words, because that's what they call them in the specification. Use 64-bit words. We call these A through H during the round computations. They will be in the initial values of A through H. And so we will start the round by initializing, A through H to be these values here. And in SHA-256, we work with 32-bit words. In SHA-512, we work with 64-bit words. Okay? All right. Then we have to do some block expansion. So we process the file in blocks of, either 256 bits or 512 bits, or if you want to think of this in terms of, 512 or 1024. And then we subdivide these blocks into words. So the first 32 bits or 64 bits, depending on which mode you're working at, is the first word, and then the next word, up through the last word, W15. And then we expand that to either 60, to enough words for each round. So for 256-bit mode, we need 64 rounds. And the words are generated by just this complicated looking XOR thing, where we look at previous words, and two of the previous words we're going to XOR different rotations and shifts of these words. So we're going to rotate this to the right or shift it to the right. Rotating takes the bits off the right and puts them on the left. Shift just pads on the left with zeros. And so we're using a combination of rotate and shift operations here. And then in 512 bit mode, we need more rounds. And because my blocks go up to 64 bits long, I want to expand some of these numbers out so that I'm shifting into some of the other bits as well. So this number's changed, this number's changed. These numbers are different, but this is, structurally the same thing as what we did here. So 256 and 512 are very similar in what they do for block expansion. Then we have a constant value that's made use of in each round. In SHA1, we only change that constant every 20 rounds. That turned out to be a weakness of SHA1. And so SHA256 and 512 use a different constant for each round. So there can be up to 80 rounds, and the constants can be 64 bits long. And so we don't have enough room on this slide to show all of these constants. But if you want to look at them, they're in the NIST specifications. There's a table on pages 11 and 12 where you can see what these constants are. And I'll show you where they get used. Okay. So another advantage of SHA256 and SHA512 is that there's only one round type. We don't have choice rounds and parity rounds and majority rounds like we had in SHA1. We just have the one round type, and I'm going to show it to you on the next slide. We're going to start by setting A, B, C, D, E, F, G, H to the 8 blocks of the initial hash. And then in 256 round mode, 256-bit mode, we're going to loop through all 64 rounds. We're going to generate some temp values. Temp 1A involves a lot of rotations. Temp 2A involves some rotations. And then, what am I looking here? Temp 1 uses that Temp 1A value plus some of these other values. Temp 2A is being used here. And and I have left off, because I'm just realizing I left off plus D here. So A, B, C, D get used in temp 2, E, F, G, and H get used in temp 1. Sorry about that. Okay. Temp 1 also uses, once we've calculated this value, we also use the ith constant off of that table that I mentioned that's on pages 11 and 12 of the NIST specifications, plus the ith block of the ith word of the input. So this is where the input is being used. Okay. And so we're using both of those as part of temp 1 as well. Okay. We're using the choice function and the majority function. We're not using the parity function here. And then once we've calculated temp 1 and temp 2, then everything shifts forward. H becomes the new value of H becomes the old value of G. G becomes F. F becomes E. E becomes D plus temp 1. D becomes C. C becomes B. B becomes A. And then A becomes the sum of temp 1 and temp 2. And then we go to the next round. That ends the for loop, or the for loop, and I increments, and we do all this again. This rotating diffuses changes in the plain text to make it hard to create a collision. And then the fact that we're applying different functions, that's what's creating confusion, so that it's not always obvious what the relationship between your plain text and your ciphertext is going to be here. All right. So in the 512-bit mode, we have to go up to 80 rounds instead of 64 rounds. And because we're using a different word size, we're rotating by different amounts here. But except for the changes in these rotation amounts and the number of rounds, everything else here is the same, including the fact that I have left off the plus D from this term here. And then this part is exactly the same as well. All right. So at the end of the round, we add the values of A through H to the corresponding blocks of the previous hash. I should say the corresponding words of the previous hash. Trying to use the terminology correctly. And if this is the last block of the message, we'll just return the hash. Otherwise, we reinitialize A through H, set it back to the initial hash value, and then process the next block. And so structurally, there's very little difference between SHA-256 and SHA-512. We just have to, work our way through the for loop with different block sizes here. So there are more bits to XOR or add here, but it's otherwise the same sort of thing. So this gets us through the rounds, and that finishes up the SHA-256 and SHA-512. Just briefly, let me tell you the other modes. 224 is identical to 256, except that it uses a different initial hash, and when you're done, it truncates the last 32 bits from the digest, so the digest fits in a 224-bit length. This mode is not widely used. It was originally around to work with some sort of legacy hardware that had some constraints that kept it from being able to use all 256 bits for a hash. It had to have some hardware check bits as well. So this is a sort of an antiquated mode, but it has not been broken. It is still valid, but it's not widely used today. And then these other modes, they're absolutely identical to 512, except that they have an initial hash that's different. And they're all different from each other. Each of these modes has a different unique hash. But once we're done, we just truncate the final digest to one of these different block sizes. And so we get the advantage of the more rounds of encryption and the possibly longer input size, but we can get these advantages with a smaller digest size. So, like I said, none of these modes have been broken yet, but these are by far the two most widely used modes. Okay? All right. Y'all take care. Thanks for watching. I will hold office hours tomorrow if people have any last-minute questions about the key expansion. Otherwise, I'll see you guys next week. Take care.